our work over here. So we actually had a couple different things that you said about the relationship between the different projection matrices that you got on your different teams. So on the one hand, Brian from team 4 is saying that the projection matrices that everyone in his team got were all the same as one another. Matt from team 5 says that that was almost true, that 2 of the projection matrices that you got in your team had opposite signs as one another. So they were equal and opposite. So how about this? How about if I quickly run through an example of choosing 2 different vectors, and we'll sort of find out how I do with this. So I'm going to pick, just for the sake of argument, I'm going to choose W and X for my 2 vectors for which to build my projection matrix. So if those are the ones I pick, then my matrix A is -2, 2, 1, 2/3, -1/3, -2/3. So that A transpose A, -2, 2, 1, 2/3, -1/3, -2/3, -2, 2, 1, 2/3, -1/3, -2/3. So if I form this product, then going across the row and down the column, -2 times -2 is 4, 2 times 2 is 4, 1 times 1 is 1, and so that's going to add up to 9. -2 times 2/3 is 4/3. -2/3 -2/3, here I get 0. I'm going to get a 0 down in this entry as well. And then when I multiply across this way, 2/3 times 2/3 is 4/9 plus 1/9 plus 4/9. That's 9/9, and that's 1. So when I choose the vectors W and X to build my matrix A out of, then this is what I get for A transpose A. And if that's A transpose A, then it turns out that that's a really easy matrix to invert. So here A transpose A inverse, because this matrix was diagonal, its inverse is just the matrix with the reciprocals on the diagonal. 1/9, 0, 0, 1. So that's A transpose A inverse. And so the projection matrix that I get using this A transpose A inverse will be A, so that's my 9, 0, 0, 1, times A transpose A quantity inverse, that was my 1/9, 0, 0, 1. And then I'll multiply that by A transpose. Oh, I'm sorry. This should be A here. So A was -2, 2, 1 in the column, and 2/3, -1/3, -2/3 in the column. Yeah, I knew something didn't look right. And then going across the row, 2/3, -1/3, -2/3. Box that up. So I would need to do this matrix multiplication. I'll do this second product here first. If I multiply by a diagonal matrix on the left, that's going to act upon the rows of this matrix. So that's going to multiply the first row of my matrix by 1/9 and give me -2/9, 2/9, 1/9. And then the second row is going to remain the same, 2/3, -1/3, -2/3. And then carry that matrix down. And working to my last row here, my projection matrix that I get should be, so first of all, it's 3 by 3. -2 times -2/9, that's 4/9, plus 4/9 is going to give me 8/9. -2 times 2/9, -4/9, minus 2/9, -6/9, that's -2/3. -2 times 1/9, that's -2/9, minus another 4/9, that's also -2/3. And then the second row is going to be -4/9 minus 2/9, -2/3. 4/9 plus 1/9, 5/9. And then 2/9 plus 2/9, that's 4. ninths. And then on the last row, negative 2 ninths minus 2 ninths, that's negative 4 ninths. 2 ninths plus 2 ninths is 4 ninths. And the last entry, 1 ninth plus 4 ninths, it's 5 ninths. So crossing my fingers that my arithmetic is correct here. I'm a little skeptical that maybe one of these entries is wrong. But anyway, so if this is the P that I got, then in the process, if we're to believe what Brian claims, then the matrix that I just got should be the same as the matrix that you all got, even if you all chose different pairs of vectors from this list to form your projection matrix. First of all, before I go any further, can somebody spot check my matrix here? Do I have any arithmetic out of place before we accept this answer and go forward? Yeah, so Brian raises the objection that my matrix isn't symmetric. That's what's causing me the problem as well. I'm a little concerned that my projection matrix isn't symmetric. Well, does it need to be symmetric though? Because we know A transpose A must be symmetric, but we haven't investigated the question of whether P itself needs to be a symmetric matrix. My suspicion is that probably it will be. So let me just double check my arithmetic. The only entries in my matrix that aren't symmetric are this pair. So let me just double check that that pair was computed correctly. So negative 2 ninths minus 2. Oh yeah, no, that's where it is. Thank you, Brian. So this entry in the upper right should be negative 4 ninths. And then I think we're good. So the first big surprise here, I think I'm going to side with Brian on this, that regardless of the basis chosen for S, regardless of the choice of basis for S, the projection matrix should be exactly the same. So that actually requires a little bit of proof, and maybe I can just quickly sketch that proof up here. So a proof of that might go as follows. Let's say I have two different bases for my subspace S. So let's call them B and B prime. So if these are two different bases, for S, then according to first semester linear algebra, we should have a change of basis matrix let's call it C, and it would have the property that the matrix A multiplied on one side by C and on the other side by C inverse, that C inverse AC would be equal to, what should I call it, A prime, the matrix that we get by choosing the columns of B prime, the basis for B prime. And then all we would have to do is show that A prime times A prime transpose A prime inverse times A prime transpose is equal to A times A transpose A inverse. times A transpose. If we can prove that, and that's a straightforward computation, then we should have what we need. On the other hand, in the channel, you're raising the question that depending on the basis that you choose, you are going to get a different A transpose A, and that I absolutely agree with. I mean, we saw examples a few minutes ago of all the different A transpose A's that your groups got. So even though the A transpose A's will be different, the projection matrix P should be the same. So although the A transpose A is different for different choices of these bases, your projection matrix P should be the same, regardless of what you have here. So let's leave that question to the side for the moment, because we want to get to the big finish of the day, which is to actually verify that this thing that we're doing gives us the projection the way that we hope that it will. So just to quickly get that set up so that we have enough time for your group to take a stab at it and then for us to look at it all together.